Hi everyone, I am Dr. Jalal Al-Anssari. I would like to present my paper ID 128 in the 4th IVPR conference in August 2020 in Japan. My paper title is the Planar Hyperplanar Rotated Polar Coordinate System and its mathematical solid vector addition, multiplication, division, dot product, and cross product operation. I wish you have a good time in this conference in Japan, and I wish you enjoy my presentation. So I'll start with the table of contents. First, a brief explanation of why we came up with the solid vector rotated polar coordinate system and its mathematical operation, introduction, contribution, literature review, rotated polar coordinate system, rotated polar mathematical operations, seventh, the conclusion, and finally, the acknowledgement. So section 1 shows a brief explanation of why we came up with the rotated polar coordinate system and its mathematical operation. That is to answer the following questions that have been surfaced after inventing the solid vector subtraction operation of what is its coordinate system, what is its hyperplane, and what are its complementary set of solid vector addition, multiplication, division, dot product, and cross product operations. So section 2 is an introduction. So the 3D and hyperdimensional curvilinear mathematical operations have a wide range of 3D image processing applications, such as developing 3D and hyperdimensional artificial intelligence and machine learning descriptors, detecting image similarities and dissimilarities, controlling of 3D object rotations in 3D space, capturing of 3D objects using CAD applications, developing indoor or outdoor navigation using vision-based GPS systems, developing vision-based obstacle avoiding applications. So Jalal Al-Ansari, Ankara Lisko, and Inam Nasser recently proposed their curvilinear solid vector subtraction operation. They used it to define the 3D gradient Laplacian unsharp and gradient-based Laplacian spatial filter geometrical edge detectors for the 3D images. They have called it solid vector because its length is unpartitioned and its direction is unpartitioned as well. So the solid vector has only two components. First, one angular component theta, and last one length component r. So next I shows our contributions in this paper. So our contributions include first defining rotated polar coordinate system based on two novel axes, the pole zero vector and the directional sign axis. Second, defining 2D, 3D, and hyperdimensional rotated polar coordinate system space. Third, defining solid vector addition. Fourth, multiplication. Fifth, division. Sixth, dot product. And seventh, cross product solid vector operations. So I'll skip the literature review because of the limited time of this presentation. That's only 10 minutes. So I'll go all the way to our proposed rotated polar coordinate system. So our proposed rotated polar coordinate system is a rotated version of the fixed polar coordinate system from the fixed two-dimensional xy plane to the freely rotating plane hyperplane in the Cartesian space around the origin point null vector, where all of its vectors are confined in the same plane hyperplane. So figure 2 shows our rotated polar coordinate system, where vector VPU is the pole zero vector, vector VPI is a vector operand in this coordinate system, theta is the angular displacement, Vs is the directional sign axis, Vt is the result of the solid vector subtraction between VPI and pole zero vector, VPIR and VPI theta are the unit vectors of the rotated polar coordinate system. So the center of the rotated polar coordinate system falls on the null vector origin point of the Cartesian coordinate system. This rotated polar coordinate system has only two axes, the directional pole zero axis and the directional sign axis. So the directional pole zero vector describes the no quantity lowest starting empty direction with respect to the other vector operands that are involved in the mathematical operation and can be one of them. So the directional sign axis, that's the other axis of the rotated polar coordinate system, is the product of the directional solid vector subtraction operation between the directional pole zero vector and the other vector operand that is involved in this operation. And it is also perpendicular to the directional pole zero axis. So next I define the rotated polar coordinate system plane hyperplane. So we define a set of vectors as said to be planar hyperplanar if a plane hyperplane in the space contains the origin point null vector, the directional pole 0 vector, and all the other vectors in this set with at least one of them non-parallel with the directional pole 0 vector. If no plane hyperplane in the space can be written in this way, then the vectors are said to be non-planar hyperplanar. So next I present the solid vector mathematical operations. First we define the term solid vector as a vector that has only two components, only one directional theta at vs component, where theta is the angular displacement and vs is the directional sine axis, and finally one length r component. So next I present the solid vector addition operations as illustrated in figure 3. The given inputs are the directional pole 0 vector VPU and the vector VT that contains the theta angular displacement and the directional sine axis VS. So first we do the directional addition, then we do the magnitude addition. To do the directional addition, we suppose vector VPI prime length equal to vector VPU. We project vector VPI prime length, V prime PI length on VPU and on VT respectively. Then we add the two projected vectors to get the direction of V prime PI. Then we add the length of vector V prime PI to the magnitude addition to get the final result, that's vector VPI. Next I present the solid vector multiplication operation as illustrated in figure 4. The given inputs are pole 0 vector V0 and VP2. So first we get to the angular displacement theta and the directional sine axis of vector VPU by the solid vector subtraction operation between VP2 and V0. Then we multiply the angular displacement theta by the angular multiplier to get the final angular theta of vector VPI. Then we suppose V prime P1 vector length equal to vector VP2. Then we project V prime P1 on vector V0 and on vector Vs. Then we add the two projected vectors to get the direction of vector V prime P1. Then finally we multiply the length of vector V prime P1 by the length multiplier to get the final result, that's the vector V P1. Next, I present the solid vector division operation. It is similar to the solid vector multiplication operation, but instead of multiplying by the angular multiplier and length multiplier, we multiply the vector by 1 divided by the theta divisor and 1 divided by the length divisor. Next, I present the solid vector dot product operation. As illustrated in figure 5, the given input is V0 and VP1 and VP2. So first we do solid vector subtraction operation between vector VP1 and V0 and vector VP2 and V0 to get the vector VT1 and VT2. So next we do Cartesian magnitude dot product between VT1 and VT2, and the result is the solid vector dot product between vector VP1 and VP2. Next, I present the solid vector directional cross product operation. It is similar to the solid vector directional dot product operation. So the given inputs are vector V0 and vectors VP1 and VP2. First we do solid vector subtraction between VP1 and V0 and solid vector subtraction between VP2 and V0 to get vector VT1 and VT2. Then we do Cartesian magnitude cross product between vector VT1 and VT2 to get the result of the solid vector cross product between vector VP1 and VP2. So finally, I present the conclusion. This research extended the recently proposed solid vector subtraction operation by defining its coordinate system. It's a 3D hyperdimensional space. Its whole complementary set of solid vector operations. The effect is that converting the correct 2D fixed polar to correct 3D rotated polar mathematical operation. The future work include, but not limited to, developing robots 3D SLAM, rotation control of objects, 3D object recognition detection, and 3D virtual sculpturing. And thank you for listening. I appreciate it so much.